Hey physics fans, welcome back. This is going to do question number 5 on page 147. A. What is a geosynchronous orbit? What is the period of a geosynchronous orbit? What is the orbital radius of a geosynchronous orbit around the Earth? Okay, so let's just take a look at orbits first. We've already talked about orbits, and there's a view from the North Pole. There's our North Pole, and there we are right there. Smile, we're right there. And see, the closer a satellite is to the Earth, the faster it goes. So this is kind of like the yellow one there that's going around really fast. It's kind of like the International Space Station. Every 1.5 hours it goes around the Earth. So it goes around the Earth about 17 times a day. That's not going to be very good for us. Okay, for what do you mean? Well, if we did a low Earth orbit across the poles, this is what we would see. We get the satellite coming over the North Pole, and it stripes down, and it covers the whole planet. Yeah, it just goes around, and as the Earth turns, it just kind of keeps mapping it out. So this is a good mapping satellite, but it's not what we want. What we want is a satellite like this that kind of stays right above. So if you're in Africa here and you wanted to use internet on the satellites, and you'd want to be able to point it up to the satellite and not have the satellite moving. But they have to orbit. They can't just sit there, because if you just sit it out there, it goes plop. But the Earth is spinning. Oh, if the Earth is spinning, then what we really want is what we call a geostationary geostationary orbit. We want this satellite to go around the Earth, and for the person on the Earth to be looking up and always seeing the same satellite in the same place. In the same place. So this is synchronized with the Earth. That's why they call it a geosynchronous orbit. A geosynchronous orbit. So going back to the question, what is a geosynchronous orbit? It's a satellite that is synchronized with the Earth so that it turns around with the Earth so that it's in the same place above the Earth at all times. What's the period of a geosynchronous orbit? That's a very tough question. That's going to go beyond your understanding. How about 24 hours? Yeah, of course, that makes sense. The Earth turns around in 24 hours. The satellite has to go around in 24 hours. So we got the period already. Okay, that's pretty good. Now, hang on. What is a geosynchronous orbit? Let's just understand a little bit more before we calculate more. We got this is a YouTube, an animation of all the different parking spots out in space that are all the same distance away from the Earth. And when they're that distance away from the Earth, they have the 24-hour period. If they got too close, they'd go, and they went too far away, it'd be even slower. At this distance, the perfect distance, they take 24 hours to turn around, and so does the Earth. So that means it's always above the Earth. What do we see when we look up? Well, if we looked up at night, we see and opened up our cameras and see it, stars would move. The stars move in the sky, but these satellites wouldn't. So this is what we see, and this is an actual video of the time lapse of a camera in Italy. And you can see that these dots are not moving. Well, they are. These are kind of moving towards each other, but this guy's staying put, this guy's staying put, this guy's staying put, and all the rest of the stars, including the moon and everything, zip by. Other satellites will zip by, but these satellites stay right above the camera. And that's perfect for those people that we want to have our communication satellites. So all those satellites that we see, satellite dishes that we see on the Earth that are pointing up, are all pointing up to the ones that are on the equator, above the equator, and go around, because then they stay in the sky at the exact same point. Okay, so now back to here. How do we solve this? What is the radius? Now the radius means to the center of the circle, so that's right into the center of the Earth. So there's the Earth, and we want to know that radius to that. So we go, okay, what's creating it? That's gravity. And we got our centripetal force, which is m 4 pi squared r over t squared. And the force of gravity is g m m over r squared. And we're trying to find out the period, the t. So the mass of the satellite doesn't matter, but the mass of the Earth does. So when we solve for this, we get t squared is equal to r cubed, because the r comes up here and becomes r cubed, and then we get 4 pi squared over gm. Now, that's up to you now to figure it out. Oh, we want the radius. Oops. And we have t, so I have to go around the other way. I'm solving it the wrong way. But this has to be 24 hours. But we have to do it in seconds. So this is 86,400 seconds. And then we have to solve for r. How do you do a cube root on a calculator? Because when you solve for r, you're going to get r cubed is equal to t squared gm over 4 pi squared. And you'll use the g that we talked about in the m for the mass of the Earth, and t squared, so 86,400 squared. But how do you do r cubed? Well, on my calculator here, which is an interesting one, cube is really deep into the math function. So if I wanted the cube, like the cube root of 27, I'd put it to the power of bracket 1 divided by 3. So the cube, to the power of 1/3 is a cube root, and that'll be 3. Yay! But so this will give us the height above the atmosphere. No, this is going to give us the radius. So solve it out, try it out. It's a great question. Thank you.